Today's lesson is on polynomial functions, and these go right along with the power functions that we have done previously. So the general formula for the family of polynomial functions is given by the following. A sub n times x to the n plus a to the n minus 1, or sub n minus 1, times x to the n minus 1, plus eventually we get to a sub 1x plus a sub 0. So what's happening now is we are just writing this in terms of our highest degree to our lowest power. And eventually we get to the constant term. So each power function in this sum is called a term. So each of these are power functions. This one, those are called terms. Now the constants that are in front are called coefficients. The last term without a variable is called the constant term. The term with the highest power is called the leading term. And to write it in standard form, we always arrange the highest power to the lowest power going left to right. And this is all common knowledge that most of this you've done before. Okay, so you got to have your calculator handy because it will help. Which of the following are polynomials? For each, state the degree, the leading coefficient, and the constant term. Well, this one in particular is not a polynomial because a polynomial ends at the highest power being, or lowest power being 0, x to the 0. So this is not a polynomial because we have that x to the negative 1. Okay, what about g of x? Is that a polynomial? Well, if I switch these two, then yes, it is. 3, 2, and then there's no 1, and then the constant is a 1. So the highest power is a 3, so it's cubic. The leading coefficient is radical 2, and our constant term is 1. And all we're doing is sharing those answers to those questions. State the degree, the leading coefficient, and the constant term. So what about this one? 2 times x plus 5 times the quantity x plus 5 times the quantity x minus 1 squared. Now we're supposed to state the degree, the leading coefficient, and the constant term. Holy cow. Now you can read through this with me if you'd like. This is a polynomial because we can square x minus 1 and then FOIL and distribute the 2, or we can try to decipher it all from what we see here. Well, this is a 1 and this is a 1, but if we square x minus 1, it's going to be x squared. And when we take x times x squared, lo and behold, we'd have x cubed. So without even doing the math or doing the workout, we know it's going to be a cubic function. It just is, because this is going to be x squared minus 2x plus 1, and then when we multiply by x and by 5, it's going to be x cubed. Okay, and that is explained all down here. Now, what's that coefficient? Well, it's still going to be x times x squared, which is x cubed, and then we could distribute the 2, so 2 is going to be our coefficient. So we got our degree, 3, so it's cubic. We got our coefficient, which is 2. Now, what's our constant term? Well, we're going to square negative 1, which is 1. We're going to FOIL, or we're going to multiply this 5, and that's going to be a 5, but then we also have that 2. So I'm betting that that constant term is 10. And you can go through and physically do it, but I wouldn't want to do it. I think it's pretty obvious. Now you could check my math and do it all, but I'm pretty sure that constant is going to be 10. It's a cubic, and the leading coefficient would be a 2. Now, like the power functions from which the polynomials are built, they're defined for all values of x, obviously except for polynomials of degree 0, which x to the 0, remember, was a special case. These have no horizontal or vertical asymptotes. Polynomials do not. They're smooth, they're unbroken, and the shape of the graph depends on the degree. Now remember, all positive powers look like a U. So we're looking at this quartic here. Not all quartics look like that, guys. They could look like this. But there might be some stuff going on as we zoom in. All cubics and quintics and seventh and ninth, remember, look like a chair function. So it's just unique to what the problem is. For instance, 4x, f of x equals 4x to the fifth minus x cubed plus 3x squared plus x plus 1. Now, it says on your calculator, graph x squared, x cubed, and x to the fourth. What do you notice about how each graph increases? What do you notice? Well, I think you notice that they increase faster the more we add a variable, or a power, I mean. Now, in general, power functions with larger positive powers eventually grow much faster than those with smaller powers. And that's going to tell us about the behavior of polynomials for large x's, like 5. So if you just imagine this, for example, what if x is 100? If we put 100 in here, 100 to the fifth is, times 4 is a big number. Was that 40 billion? 40 trillion. No, 40 billion. Now, if we put 100 into all the other terms, they only add up to negatives 969,899. All the other ones. So this is clearly the most influential part of the polynomial, is the leading term. So because 40 billion minus 100, minus a million is still 39,999,000,000. You know what I mean? So as you can see, it is by far the most influential part. And that we call, ladies and gentlemen, the long-run behavior of polynomials. And we talk about limits of those in order to discuss the long-term behavior or the long-run behavior of our polynomial. We only have to use the limit of the first term. Now, zeros of polynomials. So if we're given this polynomial, 3x to the sixth minus 2x to the fifth plus 4x squared minus 1. Well, obviously, if you put in 0, you get negative 1. So you know you're below the x-axis. But we also know from the 6 that it absolutely has to be some type of U-shape. So the question here says, is there a reason to expect a solution to the equation q of x equals 0? In other words, do we have zeros? If not, explain why not. If so, how do you know? Well, we know because this tells us it's U-shaped. Therefore, it has to have zeros because it dips below the x-axis. So, kind of interesting. You also know it has to have one negative and one positive in order to be a U-shaped, because it's going to go through the y-axis. Okay? Now, let's find some limits. What is the limit of 4x cubed minus 2x squared plus x minus 1? So this is a cubic equation that's positive, so it's going up. And we only have to look at this to figure out the long-run behavior. So as x approaches infinity, I just need to look at this term. Well, it's x cubed, so it's going to be infinity. So it's going to approach infinity. Similarly, this one is a x to the fourth, which means U-shaped, but the negative tells us it's going to go down. Now, I want to know the limit as x approaches negative infinity. What is our graph approaching? It looks like it's going to approach negative infinity. Now, this is the actual graph. Notice I just made a U. I don't know what the humps and all this stuff is. I don't care. I'm just looking at this leading coefficient and this leading power. So I know what the long-run behavior is based on that. Our problem set is on page 448. We're going to use a calculator on some of this. 1 through 11, 15 through 21, number 25, 33 through 36.